Alright, question 3 says, what is the pH of a 0.5 molar aqueous base solution at 25 degrees Celsius? And then for the weak base solution, it gives us the Kb. So we can make up an equation here, and we can say weak base is going to react with water, and then bases are proton acceptors, so we're going to end up with Hb with positive sign over here, and we're going to end up with some OH minus. And the thing that we're interested in to find the pH is the OH minus right here, because if we find the OH minus, now we are into the pH square right here, and we can go from there to the POH to the pH. So that's the thing we want to find. So initial change equilibrium, and we're told that we have a 0.5 molar solution, none, because this is a pure liquid, and we have to assume that there's none of this to start with and none of this to start with. When the change takes place, we're going to lose X amount of this, and we'll gain X amount of this, and we'll gain X amount of this. And so we end up with 0.5 minus X, X, and X. And then we can write the Kb expression, and Kb is equal to 3.8 times 10 to the negative 6 that tells us, and that would equal the products, which would be X squared divided by reactants. And let's assume that this X is small in compared to the 0.5. And then let's solve for X. And so then when we solve this guy for X, it turns out to be 0.00137 molar. And then once we find that molarity right there, that puts us into the pH square, because that's the OH minus ion concentration. And then we got to get to the POH and the pH. So we have to negative log that. And so the negative log of 1.37 times 10 to the negative 123 would end up being 2.86, and that's our POH. And then do 14 minus that 2.86 to find the pH, and the pH then would equal 11.14, which makes sense because it's a basic solution, so it's above 7. All right, our next problem is a G, K, and T problem from chapter 19. Here's a reaction. It says it has an H and it has an S. Watch the units here. Be careful, because this one's in kilojoules and this one's in joules. Okay. Find G and K for this reaction at an absolute temperature of 600 degrees, and then assume that H and S are independent of temperature. And so for this, you'll want your equation sheet, and on your equation sheet you can find your calculations for G and H. And I seem to have misplaced my equation sheet here. Anyway, I can just write down the equations for you, but G is equal to H minus TS, and usually you'll see triangles in front of these because each one involves a change in Gibbs free energy, a change in the enthalpy, a change in the entropy, and then just match up the units and be really careful with them. So H is 375.3, and notice that's in kilojoules, and then T has to be the absolute temperature, and so that's 600 Kelvin. And then S is 175.7, but that's in joules, so move that 1, 2, 3 to the left, so you have 0.1757, ignore that one right there, and then now we're in kilojoules per mole right here. Take those guys, multiply them together, and then subtract them from 375, and we end up with a G equaling 269.9 kilojoules. Now to find K, G is equal to negative R times T times the natural log of K. And so once you know G, which we know that right here, and we know R, we can look that up, and we know that the temperature is 600, we can now solve for K. So let's plug these values in. G is 269.9. Remember, that's in kilojoules. And then the R has to be in kilojoules as well, so make sure that you have that as 0.00831 kilojoules per mole Kelvin. And then the T has to be 600 Kelvin, and then we're doing natural log of capital K right here. So solve this part first, and then you have to undo the natural log on your calculator. And let's do that on our calculator so you can see how that's done. So first of all, 269.9, and then let's divide that by a negative 0.00831. Let's hit enter, and then let's divide that by 600. Hit enter, and so we have, I'm just going to rewrite it down here, ln of k equaling our negative 54.13. Now we want to find k, so we have to do the 10 to the x key, because it would be 10 to the negative 54.13 to find out what k is. And so I'll do 10 to the x, and then I'll do a second answer, and we'll hit answer right here, and we get a big, huge number of, I got 7.3 times 10 to the negative 55.
Isn't ln e to the x?
Oh my gosh, yes. Thank you very much. Fortunately, I had somebody here to tell me that this ln right here would not be 10 to the x key. It would be the e to the x key. Thank you so much. I saved my video there. And so let me go back here to do this part of the calculator. And this should be the e to the x key, not the 10 to the x key. If it was regular log, if it was log, then it would be 10 to the x. But my apologies. Let's go back and let's do the e to the x key, and then that would be negative 54.13 in there. Enter, and now I get 3.1 times 10 to the negative 24th. 3.1, enter exponent to the negative 24th. And since it's k, an equilibrium constant, it doesn't have any units. It's just the exponent's number. All right, is this reaction spontaneous? Well, to be spontaneous, it has to have a negative g, and so the answer is no, it is non-spontaneous. And above what temperature does this reaction become spontaneous? Well, now we need to do a second g equals h minus ts. And we're going to look for this guy. We're going to look for temperature. And what we want to know is, when is G going to start to turn negative? Because when it turns negative, then we know it's spontaneous. And so we'll set G equal to 0, because that's as close to negative as we can get. And technically that's when we're at equilibrium, and we're just at the tipping point of becoming spontaneous. And then we put in the H that we calculated up here, which was 375.3. That's in kilojoules. Minus T, that's what we want to find in Kelvin, and then make sure that our S is in kilojoules, which is this 0.1757 kilojoules. And now we solve this equation for T, and I'll let you guys do the calculator because I screwed it up last time. And so you should end up with 2,136 Kelvin is the temperature at which it just starts to become spontaneous. We're at equilibrium and we're right at the tipping point where it should be spontaneous. All right, more on the next one.